Okay, since we are focusing on oceanography here, we have to come back to surface winds. But first, let's look at another aspect of zonally asymmetric regional circulation, which is the important Walker cell, which nicely connects also how the ocean forces the atmosphere, or how the atmosphere responds to the ocean forcing. We looked at sea surface temperature distribution, so we have critical warm pool here, upwelling, pushing water, Ekman divergence, creating cold tongue here. We looked at it in terms of the OLR and sea surface temperatures, and now we are looking at the associated warm temperatures that form on this side, the Indonesian through flow that we briefly mentioned, and the Indian side of the warm pool. And obviously warm sea surface temperatures drive a strong response in the atmosphere when the sea surface temperatures are above the convective threshold that we had marked with 27 degrees C isotherm, and we had also looked at the 5 millimeter per day precipitation contours. So you can see this massive convection over the Western Pacific maritime continent, referred to as the boiler box by Ramage in the 1960s. All kinds of interesting processes happen here, including intra-seasonal processes of communication from the Indian Ocean into the region, across, and then back over, and of course the monsoon circulation and so on. And you have probably seen this as we did before, in the context of El Nino, when this entire convection system begins to move eastward during an El Nino and gets pushed more westward and confined during a La Nina, which we'll come back to at the end of this chapter. So this rising motion hits the tropopause. As we know, the air cannot easily cross the tropopause, where the temperature gradient changes direction in the stratosphere, warming because of ozone formation and UV absorption. So just like there is a zonal mean meridional split in the poleward direction leading to Hadley cells, there is a zonal split leading to the Walker cell. Sir Gilbert Walker, who was a East India Company officer in India in the late 1800s into 1900s, was worried about the famines in India, and he sat down and figured out that it was related to a pressure oscillation between Darwin and Tahiti, which he called the Southern Oscillation. And later on in the 1960s, Jacob Bjerknes pointed out that the Southern Oscillation and El Nino were the same, so now we refer to it as El Nino Southern Oscillation, which we'll come back to in a minute, and we have already looked at several times, and I have many podcasts on it as well. So this zonal split results in a subsidence over the East Pacific, again corresponding to cold temperatures, high pressures, dry weather, and so on, which extends entirely across the west coast all the way into US, Central America, and South America. Cold upwelling, fisheries production, etc. here. And the other part of the sinking happens here over Western Indian Ocean, and there is the West African monsoon and the Amazon convection. So you have the Pacific Walker cell and the Atlantic part of it and the Indian Ocean part of it, all of them oscillate back and forth at seasonal and interannual and decadal and global warming timescales. So that's a clear example of the atmospheric response to SST distribution as well. This is a coupled problem because the sea surface temperatures themselves are determined by the atmospheric forcing, and then atmospheric forcing responds to it, and there is a feedback that settles into the climatological zonal gradient, and of course the western boundary currents, Indonesian through flow, and so on, which then have zonal modes of variability on some time scales, 2 to 7 years for the El Nino, much more episodic for the Indian Ocean dipole or zonal mode here, and also episodic for the Atlantic zonal mode on this side. So because the zonal extents of the basins are also very different, the life cycles of the zonal modes, which are coupled modes like the El Nino, Indian Ocean Dipole, and the Atlantic Nino, are also different. These only last for about 3 months, whereas this one has 9 to 12 or even 18-month life cycle. And there are interactions from the Indian Ocean to the El Nino to the Indian Ocean, Atlantic Nino to the El Nino, and El Nino to the Atlantic Nino, and so on. All that is related to ocean forcing by the surface wind stresses. Here we are looking at June and December, which gives you a good sense of the annual cycle of the winds. These are climatological winds averaged over 1988 to 2017. So colors are the wind speeds and vectors are of course wind vectors. And you can clearly see our own Indian Ocean region here. During the boreal summer months you have land heating, low pressure which sets off the monsoon, and then the monsoon heating itself demands moisture, most of which comes from south of the equator, and a lot picked up here over the Arabian Sea. So wind speeds in the so-called low-level jet or the Findlater jet can be very strong, and the Indian Ocean has southeasterly trades in the southern hemisphere. The northern hemisphere obviously is dominated by seasonal changes of the monsoon circulation. Southwesterlies here and northeasterlies here, where the winter cooling, cold temperatures, high pressure, and warmer ocean, low pressure drives this flow. And then you have to add Coriolis, of course, to get the northeasterlies here and the southwesterlies here. You have the southeasterly, northeasterly trades crossing the equator here into the ITCZ, and of course where the winds come together, wind speeds are minimum, so you can see the weak wind speeds here in bluish colors. And on the Whirlpool also latent heat loss is reduced, so the trade winds die off and you begin to get into the monsoon regime on this side here. So you have weakened wind speeds here over the Indo-Pacific Whirlpool throughout the year, and you can generally see that the wind speeds over land tend to be weaker compared to the ocean in general, especially over the Southern Ocean, where during its winter the winds are much stronger than during its summer because of the equator to pole temperature gradient and the related energy transports and so on. You can clearly also see the westerlies and the trade winds giving us the subtropical gyres circulation here and the subpolar gyres. What else can I point out? The wind stress curls, as we will see, will be critical to drive convergence, downwelling, or divergence, upwelling, as well as spare transport. So when there is wind stress curl forcing at the surface, it turns out that the water transport is induced. In a simple way, you can think of it this way. Winds are pushing the water westward here by the trade winds, so Coriolis is going to push the waters northward, and by the same token here winds are pushing it eastward, the ocean currents, and Coriolis will deviate it southward, but the Coriolis increases from this side to this side, so the southward transport F times U integrated over the Ekman layer or the wind driven transport layer will be more here than here, so there is a net southward transport because of the Coriolis pushing more water southward here than northward here. So that's a simple way to think about why this wind stress curl. If you curl your fingers around the westerlies and the south northeasterlies, you get a thumb pointing downward in the negative Z direction. So the wind stress curl is negative, and that's forcing a southward sphere of transport. Okay, also that means winds are putting negative vorticity into the ocean, so the mass transport has to be balanced by taking the water northward somewhere and generating positive vorticity somewhere, because wind is generating southward transport and negative vorticity. You have to balance both, and that can only be done on the western boundaries. So you get strong western boundaries here in the Pacific as Kuroshio, by the same token here as the Gulf Stream, and similarly you get southward western boundary currents here, the Oishio current and the Labrador Sea current, Labrador current. Of course, the Indian Ocean has western boundary current which is going northward here but southward here, so it is completely reversing signs. And there are western boundary currents here in the East Australia current, the Brazil current here. The eastward current, eastern boundary currents by the similar dynamics tend to be broad, weak, and shallow, whereas these are strong, narrow, and deep boundary currents here. I'm just introducing that here as additional dynamics, which is covered elsewhere in my oceanography course or the dynamics course that you can follow up. Okay, so divergence of the wind then is just a gradient dot tau, which is del tau x plus del tau y, del tau xx plus del tau yy, which looks like our del u del x plus del v del y. So divergence, but this is slightly different. And the curl, it's what I mentioned here, it is del tau y del x minus del tau x del y. You can do the matrix operations, I'm sure, to figure out these both simple vector calculus. So this is what drives the spread of transport in the ocean. And also this looks like del v del x minus del u del y, which is vorticity in the ocean or the atmosphere. And as I said, wind stress curl tends to produce vorticity in the ocean as well. Okay, so you can see the similarities there. Okay, so this is the annual mean surface zonal wind stress, meridional wind stress, and wind stress curl here, and the divergence of the winds, that wind stress that we are looking at. So obviously wind stress, you get strong trade winds in both hemispheres, and the trade winds here, and the weak annual mean winds here, which is very different than these two northern hemispheres because of the monsoonal forcing. And by similar token, you can see that the tau y is strong here in the southeasterly trades in both hemispheres as well as here, but the northeasterly trades are only strong here. They don't extend as far here as we saw before. The ITCZ, the Whirlpool, weak winds here, etc. begin to change the dynamics here, whereas the zonal winds extend much further west compared to the meridional winds. And you have the westerlies, strong westerlies showing up here. The meridional winds associated with them are much weaker compared to the trade winds here in the tropics. Okay, curl of the wind stress again negative here. By the same token, by changing the sign of the Coriolis, we get positive curl here if we do right hand rule, but because of the change in sign, we have to do the left hand rule, so that you still get negative wind stress curl northward spread of transport, negative vorticity going into the ocean, mass balance happening again at the western boundary here. Of course, the western boundary current here is different, as we said, because of the Indonesian through flow setting up a pressure gradient and the lee wind current going against the winds and producing not a very strong upwelling here, unlike the strong upwelling we have here and off of Namibia here. So quick differences there. And of course the North Indian Ocean is again different because of the curl. It doesn't make much sense to look at the annual mean in the Northern Indian Ocean because of the strong seasonal changes, but nonetheless we are doing that here just to look at consistently here for the global picture. And the ITCZ of course shows up as the wind stress curl, which lifts the thermocline, makes the mixed layer shallower and warmer, and then you put freshwater flux on top with rainfall, which stratifies the ocean and amplifies the warming, which maintains represents the ITCZ and the warm temperatures and the convective feedbacks and so on. If you look at the divergence, of course, you have strong divergence, convergence coupler here across the ITCZ, and you have divergence happening as the trade winds come across, have to turn around and meet the ITCZ here. So you can see some turning around here and some crossing of the equator meeting the ITCZ here. So the convergence in the ITCZ is clear in both the Atlantic and the Pacific, and a little bit in the southern part here. This is a little bit different just because it's so close to the equator, and there are details that we won't get into. Okay, so that all follows. The SPCZ also shows up here. The Indian Ocean Marine ITCZ shows up here, which remains throughout the year, as you remember from the precipitation picture. So here is the annual mean zonal mean profiles of wind stress and derivatives thereof as indicated in the labeling in A, and in B we are looking at longitudinal profiles of annual mean meridional wind stress tau y in red and blue profile, the zonal gradient of meridional wind stress delta y del x, and the full two-dimensional wind stress curl shown here in this picture in the B here. Okay, so this is just kind of confirming the mean annual mean, zonal mean profiles of wind stress. What do you see? Of course, the southeast northeast trades and the and derivatives thereof. So I won't go into the details, but obviously you will see del u del tau x del y and del tau y del y. The meridional gradients of zonal and meridional winds are important for the terms that we have looked here in terms of curl and divergence of winds, but basically they confirm the maps we have seen. For wind-driven dynamics in the ocean, these are obviously critical, and they correspond to things like where the wind stress curl goes to zero, where you get the north equatorial countercurrent and south equatorial countercurrent, and separation of the western boundary currents, and so on and so forth. Okay, so that corresponds to this as well here. The full two-dimensional wind stress curl in gray along 38 north, roughly the latitude of San Francisco, USA, and Lisbon, Portugal. So you can see at 38 north, if you draw a line going in longitude from 150 west to the Greenwich meridian here, or back to the dateline here. So they on the western boundary side should correspond to approximately the separation of the boundary currents from the coast, becoming Kuroshio becomes the North Pacific current, Gulf Stream becomes the North Atlantic current, and so on. Okay, so let's leave this here as a quick look at the wind patterns and their impact on the wind-driven ocean dynamics. Very quick introduction. If you want details, you have to look at my oceanography course or the dynamics course, but we will look at atmospheric response to ocean forcing in a bit more detail, with the example of El Nino as one example, but we will look at some of the basic processes that are involved in atmospheric response. Okay.